All right, we're going to start today with solving systems by substitution. That's the goal. And first, graphically, we're going to talk about the vocabulary. So if two equations are considered inconsistent, what will you see when you graph them? Yeah, two parallel lines. Absolutely. And if two systems are considered to be the exact same line, what will you see when you graph them? Like, how would you describe this blue line and this pink line here? What? Yeah, overlapping, one on top of the other. How many times is that pink going to hit that blue? Every time, every single time. So that means it has two vocabulary words. It's consistent because it hits at least once, but it's really dependent because it hits every single time. And then the last one is what we will spend most of our time with. These first two will be the special cases when you see them graphically. This one will be what we spend the most time on. There will be one solution because it's a line and a line. It will be consistent because it hits at least once, but it will be independent because they do not hit every single time. So these 5 vocabulary words you will use not necessarily on all the homework, but sometimes to describe the solutions. So today we're going to start with the substitution method, and we will start with this problem. So if you will write this problem down, 2x plus y equals 1, y equals 3. And we're going to find out that the solution is negative 1, 3. We're going to solve it algebraically and then check it graphically or prove it graphically. Now, because y is already equal to 3, what do you think we're going to do with it next? Yeah, we're just going to plug it in, absolutely. Substitution property. So 2x plus 3 equals 1. Then we will subtract 3 from both sides. And we will get 2x, these 3 and negative 3 will make a 0 pair and cancel. 1 minus 3 is negative 2. Then we will divide both sides by 2, and x will equal negative 1. That became the first coordinate, or the x of your answer, and we already knew the y of the answer because it was given at the very beginning. Next, we need to look at what happens to check it. Now, of course, you could plug it in, negative 1 and 3, and make sure that when you plug negative 1 and 3 in that it would be 1. But I want you to prove it algebraically. So the first thing you have to do is get y by itself. So we subtract 2x from both sides, and y1 will be negative 2x plus 1, and of course y sub 2 in the graphing calculator will be equal to 3. And I've already written up here where you're going to go. You're going to go to y equals in your calculator. So let's do that next. Once you get that written down, let's go to y equals next. Does anybody have this little X box on in their calculator? Do y'all know how to get that to turn off? You arrow up to it, press enter, and then I just clear out whatever's in the X's, and then I go back to the Y's. So if your little X was on, we'll have to turn it off. So we want to plug in the little negative, not the minus sign, negative 2x plus 1 in y1, and y sub 2 should equal 3. Zoom 6 in case the last person who used it before you messed with the window. Zoom 6. And then we are going to find that intersection. So go to second trace, and which one of those means two things are hitting each other? 5. Since we only have one hit, you don't have to move the cursor like we did when we were finding mins and maxes. So you can just press enter through each one of the text messages in the bottom left-hand corner. And did we confirm our answer, negative 1, 3? If you go to the second graph button, another way that you can confirm your answer is to look at the table if x was an integer, and what is true about both the y's when x is negative 1. Did that happen anywhere else in this chart? Did the y's match anywhere else in this chart? No. So you have, if it's an integer, because I have our table set to use integers, then you could use the chart. But if your x is not an integer, then the graph will be what you want to use to make sure that your solution is correct. So that is your check step. And we did get -1, 3. Next, let's do one of our special cases. I have it written out for you, and then we're going to talk about it after you copy it down. Special case. We have y1 and y2 are 2x plus 3 and 2x plus 3. Algebraically, if you solve it all the way through and set 2x plus 3 equal to 2x plus 3, I got down to 3 equals 3. Because it is true, it means they are the same line. Well, most of you figured out they were the same line the first second I flashed the problem up there. 2x plus 3 is equal to 2x plus 3, which means there are infinitely many solutions. Make sure you have all of this written down, because it will come out true if it's an infinitely many, where if it's no solution in a minute, it's going to come out false. So let's do our check step in the calculator, and you have one extra step to do when we're checking things that you think are the same. 2x plus 3 and 2x plus 3. Seems a bit redundant, but go to the left of y2 to where your cursor is blinking on the line. Press enter once, and what happened to the line over there? Got bold. Perfect. Perfectly said. Zoom 6 it or graph it, and what should you see happen? Make a prediction. What's going to happen? It should go right over top of it as mine did. Did yours do that? Did yours go right over top of it? What if it ended up to the left or the right or higher or lower? What would you know? That it wasn't really true, was it? Okay. Or there's a mathematics mistake somewhere in the problem. Good. All right, the other special case is, what if they are parallel? So case 2 is a special case. They're already solved for y. When you set them equal to each other, because they're equal to y, what do you get? 3 equals -6. When that comes out false, you know it's no solution. Therefore, when we graph them in a second, what should we see? Yes, we should see parallel lines. Anybody need more time to write special case number 2? I'm going to write that here. This was special case number 2. The other one was special case number 1. And this way, in a very quick morning, you'll see all the ways it can come out or turn out. 2x plus 3, 2x minus 6. I'm going to leave him bold. When I graph it, I do not want him to lie on top of the other one, or I wouldn't be correct. It wouldn't be parallel. Algebraically, why do you know these two are parallel? They have the same slope from the very, very beginning. Two different y-intercepts, but the same slope. Let's do one of the homework problems that is not nice and pretty like the notes I made up. So we have two equations in number 3 on the homework. The first thing you're going to do is solve for the easiest variable. What is the easiest variable to solve for in the second equation? Why? Yeah, there's no number in front of it except for 1. Perfect math language, though. You said coefficient. Good job. So x equals negative 4y plus 2. Now that I know that that guy equals x, everywhere that I have an x in this equation, what can I now say? What does x now equal? Good. So when you plug it in, it's not quite as pretty as the examples I gave you earlier because we solved them both for y and set them equal to each other. In this case, what we're going to do is everywhere there's an x in this problem, we're going to replace it with negative 4y plus 2 using the substitution property. If you wanted to do what we did earlier, you could certainly solve both of those for y and set them equal to each other, and there would be no problem with that. Use the distributive property, negative 8y plus 4 plus 5y equals 7. What do I have to deal with first, Riley, over here? Riley G. Good, perfect. So we have to gather our like terms. What's next, Tate? Perfect. Divide by negative 3, and now we know half of our answer. Y equals negative 1. Wes, how do you suggest I get the other half? Okay, so I'm going to plug it in. Which one would you plug it in for, Wes? Y1 or Y2?
Y2.
Okay, he chose Y2, so I'm going to back substitute into x plus 4 times, now I'm going to use y as negative 1 equals 2. So we have x minus 4 equals 2, add your 4, x equals 6. So my final answer is 6, negative 1. Now if you go back to the vocabulary from the beginning of the lesson, how will you describe it when you get one solution? What are the two vocabulary words? Good, consistent and independent. That's perfect, Selena. How will you check it? Now this takes a minute or two more because what do they have to be equal to put them in the graphing calculator?
Y.
So on this moment of a check step, that's going to be y1. Then I'm going to create my y2. These are not as nice and pretty as the ones I created for notes. Make sure you have all that written down because to do the check step in the graphing calculator, those have to be written down. Now when you look at mine in my graphing calculator, make sure that I have not copied one wrong from my paper to the calculator. And you always want to recheck them at least twice to make sure you've copied everything to the calculator exactly as it should be. Zoom 6. See if you see a hit within the window. We're expecting it to be right 6 and down 1. It does appear to be there. Let's check it. Second trace, number 5, enter, enter, enter. And we got the same answer, 6, negative 1, graphically as we did algebraically. And so add just that you did a check with your GC, and it also confirmed 6, -1 was your solution. I would like to do number 4 from your homework together, because again, it's not neat as a pin like the ones that I made up for notes. So we have 2 equations. 3x plus y is 16, and 2x minus 3y equals -4. Hunter, what would be the easiest to solve for, the left one or the right one? Yeah, because y is already by itself, so. What would y be equal to in this equation now by substitution? Chloe, what do you think? What would y be equal to now? Read me this expression. Perfect. So we are going to plug this everywhere in the other equation that we have a y. We're going to put -3x plus 16. Why? Why did we do that? Does anybody know why we did that? Harrison? Correct. And if we don't get them to the same letter in the equation, we can never find one letter so that we can go back substitution to get the other letter. Good, good, good. So we're going to start with the distributive property here. So -3 times -3 is positive 9x. -3 times 16 is -48 equals -4. Now what do I need to do, Keandre, to that line? Good.
Teachers, excuse this interruption, but could you please send any freshmen who need to have their pictures either retaken or made at this time to the gym lobby? Thank you.
We've done all this work, and how much of the answer do we have? Half of it. And then what do we do with x equals 4? Which one do you want to use, Harrison? I don't care. Y1 or Y2? All right, so let's go back to Y1 and back substitute. 3 times 4 plus y is 16. So all I did was substitute out my x, and his replacement was 4. We think our solution is 4, 4. What is the last step we do before we leave this problem? Check it graphically. So we've already got y1 into the format that we want from the earlier work we did. Now we just have to get y2 in the format we want. So we have 2x minus 3y equals -4. Subtract your 2x from both sides. Divide by -3. So your y2 looks like this. Your y1 looks like that. In my first equation, in my calculator, I'm going to type in -3x plus 16. The second one takes a minute or two more because of the fractions, but I already had fractions last time. So it's just a matter of kind of replacing the old fraction with the new fraction. Make sure you have that second y2's work written down. Then when you plug it into your calculator, always double check it at least twice from your paper and your work to make sure that you've copied exactly your work back into the graphing calculator. Zoom 6 it. We think it's going to hit at 4, 4. Second trace 5, enter, 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 and sure enough, we did correctly check it and work it originally. So you have 3 and 4 finished for your homework already, and then we will do the rest. You have about